Okay, so Christophe Basso,
I'm here.
you're there and ready. Excellent. So Christophe is one busy dude. I have no idea anybody can write 10 books about anything, much less 10 books about switching powers applications. And yet they're so good. And yeah, they're just great. So unfortunately, in the process of doing some of those, he's created a whole bunch of, templates using SIMPLIS for different topologies, control schemes. And so he's going to share a little bit of that with us today. So Christophe, appreciate you doing this.
Merci, Tom.
Ouais.
Yes, so good morning or good evening, everyone. So my name is Christophe Basso, as Tom kindly introduced me. I'm going to try to slow down the pace so that you can understand my Inspector Clouseau accent, which is rather thick usually, especially at the end of the day. So what you can see on the screen right now are the templates that I've designed for, let's say, testing the transfer functions that I was deriving on the upper side book that you can see, Transfer Function of Switching Converters, in which I have explored the small signal responses of many switching converters, whether they operate in CCM, DCM, voltage or current mode control, COT, FOT, whatever. So what I was doing is I was using an average model, a small signal average model, from which I was deriving the control to output transfer function. And I was comparing the AC response of what I was obtaining with MathCAD or another solver you can think of with SIMPLIS, actually. So for that purpose, I have developed several templates using SIMPLIS, and I have enriched these templates with many more examples of switching converters that I came across for, let's say, solving customer issues or just for the sake of having more switching examples. And then I use these examples because you know that I've tried to develop a small, let's say, specialty in loop control and small signal analysis. I've just released another book that you can see with the blue cover, and it's essentially covering loop control and small signal response of switching converters, the way you would close the loop for reaching good phase margin, gain margin, and crossover frequency. So I have all these templates that I've used for exemplifying all my design examples that I have in this book. So let's start with one of these circuits. Here you see it's a boost converter built around an LM5155. And what I like to do, and that's the way I work, and whether it's on SPICE or in SIMPLIS, but mainly SIMPLIS, what I do is I start with the simplest possible model. So using, let's say, classical switch, very basic cycle by cycle circuitry, and then I test the electrical integrity of this circuit, making sure that it converges and delivers the right voltage and current at the given operating point. And once this is working okay, I start to enrich the models by putting a MOSFET model if you want, or a GaN transistor, because you can also import this type of SPICE subcircuit into SIMPLIS. Also, something that I favor, and we'll show that in a moment, is these blocks here. I like to automate things. It means I'm trying to explore different compensation strategies, and by compensation strategies, I mean poles and zeros, which are there to neutralize the variability of the usual offenders. These offenders being, of course, the load resistance, the ESR of the capacitors, all the parasitics that are going to move during the production process or the converter operating lifetime. And you have to make sure that stability is always correct in terms of phase margin and gain margin and crossover frequency while these elements are moving. So the goal of the compensation strategy is to neutralize these stray elements. And you do that I do that here by automating, as you can see on the right side, here using a control block and not the F12 window, because I like to see things on the schematic. So here we're going to immediately see a working example. So you can see I have one body plot to extract the open loop gain of my power supply. I like also to look at the compensator transfer function. I mean, all the guy here that I'm designing, what is its own AC response? And then here, the cornerstone of any analysis is the control to output transfer function of your power stage. So if I run here the simulation, the first thing that you need to check is the correct operating point, as Tom mentioned several times. And it's the same as in SPICE, you know, when you have an average model, before you consider the AC results from the average model, you have to make sure that the DC operating point is correct. So here, I was expecting an output voltage of around 24 volts with a current of 2 amps, and the feedback is around 1.8 volt, knowing that the dynamics that I have is 3 volts, so it's in linear mode. Then I look at the power stage, and this is the power stage of my power supply. So it has a DC gain of something like 30 dBs, and then I've selected a crossover frequency. Here it's 2 kilohertz. You know that in a boost converter you have a right half plane 0. So I'm calculating here the right half plane 0, which depends on the input voltage and the load current and the duty ratio. And it instructs me that 20% of this value here should be around a few kilohertz. So I read the control to output transfer function magnitude here. You can see it's about 6 dBs at 2 kilohertz, and the phase lag is about probably minus 92 degrees, 94. I enter these values here, 6 dBs and 94, and the macro, which is here, is going to calculate automatically the components value using this OTA here to cross over exactly at the selected frequency. I can look at this is a type 2. You can see it's a integrator type of response, slope -1 here. Then the 0 is going to break the slope to a 0 slope. And then a pole is going to improve the, to let's say, roll off the gain at high frequency for building gain margin. And then the phase is boosted in between. And that's the phase boost I have calculated with my macro. And then I can see that SIMPLIS is measuring a 2 kilohertz crossover frequency. Phase margin is about 60 degrees, and then 17 dBs as gain margin. Now it's easy to click here and say I would like to have instead a 45 degrees phase margin. And if I go again here, so it's again it's calculating a new DC operating point. Okay, and then let's go. You can see that the phase margin now has decreased to around 45, 46 degrees with the same crossover frequency. So it's easy now to explore different compensation strategy and look at the transient response in this case. So I'm going to look at, let's say I'm going to enable the transient source. This guy is going to be silent. And then I'm going to select a transient analysis. Okay. And here, what I do first is that I'm going to have a little bit of, okay, it's the storage depth is 2, so I'm going to accumulate the curves. And if I run here, it's fairly fast. There you go. You can see here, specific response. And now if I change the phase margin back again to 60 degrees, you see exactly what is expected. So here, the transient response, the drop that you can see here depends upon the ESR of the output capacitor, but also upon the capacitance and the crossover frequency, marginally above the phase margin. So I didn't change the crossover frequency, so the drop here is about the same. However, the recovery time here depends on the phase margin. So the more phase margin you have, so approaching 90 degrees, the more sluggish the response you're going to have, but the less overshoot you're going to, let's say, exhibit. And if you reduce the phase margin, you recover at a faster rate. However, you will start probably to have a little bit of overshoot here. The converter becomes more nervous. So you can see here how simple it is to, let's say, look at this different transparent response by exploring different scenario. And once this is done, you can go to simulator here and edit netlist. And you can see here, let me zoom a little bit, the component values that have been automated by SIMPLIS. So it's easy then to extract these components and put them on your bench prototype. And you see here the right half plane zero frequency has been calculated around 20 kilohertz. So 20% of it says that around 4 kilohertz as a maximum crossover frequency. Okay, so that's for the first example.
That's very cool. That's very, very cool.
So here, as you see, I'm a control block type of guy. So I don't like to use F12 because I like to see what's going on in the schematic. So how do you, very often I have the question that people are telling me, well, I've placed a text sheet and it doesn't work. No, you have to go from symbol library, sheet and text, and then it's a control block that you need to place on the schematic. Okay, it's not a text window. Once you have the control block, you can put whatever you want, automate calculations, and then declare a variable, either a local variable or a global variable if you want to pass parameters to the subcircuit. And once something that I found as well, or it was indicated by the SIMPLIS folks, is that to plot or access the variables that you have that have been computed by the software, then you place these control elements here. And here I'm looking at a gain, for instance, or a pole. And then you go into simulator, edit netlist after pre-process, and then you see all these parameters here that have been calculated. So that's an easy way to access them. Okay.
Yeah, when you're automating calculations, it's really helpful to make sure that the values that in what you're plotting, you're displaying in green, that's what SIMPLIS actually used for the simulation. And yep, that's very helpful.
And then, as I said, you could here with different body plots, let's say compensated open loop gain. Usually I like to have different colors and it's all symmetrically centered around zero so that I can easily, look at the phase margin and crossover frequency. And so this guy is black and this one is red for easier reading. And then I can, by changing the crossover frequency, same phase margin, you can see that with a 1 kilohertz, slightly higher drop here, which is much smaller when I have 2 kilohertz. So again, I can change phase margin or crossover frequency easily and see the effect on the transient response. Let's have a look now. I'm going to open the bug VM PID analog. So you go there, you can see all the templates on the left side, and bug VM PID analog, that this guy here. What I've done here is I've tried to reproduce a PID using the classical approach you could see in the university. It's a filtered PID, okay? Filtered PID means that the classical PID has one pole at the origin and 2 zeros. And if you look at the transfer function that is given by this PID, it's what we call a non-proper transfer function. It means that when S approaches infinity, because of the 2 zeros, then you end up having still gain going up as the frequency. It will eventually go down because of the frequency limit of the circuit, but it's not easy to meet the gain margin criteria. So what people have come up with is what we call a filtered PID. And a filtered PID is an extra pole which is added here with the n parameters. And when you tweak a PID on the bench, and usually it's the case with digital control, you can apply several methods, like Ziegler's method, for instance, where you more or less reduce the Ki and Kd coefficients to 0, then you increase the Kp coefficient until you start observing a ringing response, and it's kind of trial and error method. If you want to apply PID here to a buck converter, what I do is I place my poles and zeros either let's say automatically using the K factor or manually here using this equation here, and then I instruct SIMPLIS to automatically calculate what the parameters will be to determine the Kp, Ki or Ti or Ki and Kd parameters, and then will be passed to this circuit to see exactly what the transfer function shall be for meeting the crossover frequency that I want. And if I press here, let's go. So again, bias point is correct, 5 volt output current, and there you go. You can see the PID response. It's a nice type 3 compensator. It's a type 3 compensator because on top of the filter PID expression, I've added here an extra pole. And this second pole added to the filtered PID actually makes a type 3 compensator. A type 3 compensator is a filtered PID with an extra pole added to the transfer function. And you can see this is exactly the response we have. And I was looking here for, let's say, a 10 kilohertz crossover frequency with a 70 degrees phase margin. And if you look at the loop gain, almost 70 degrees, almost 10 kilohertz crossover frequency with the here a slightly less phase margin, probably because you know that if you start pushing the crossover frequency, then the own response of the op amp here starts to apply and then corrupt the gain and the phase boost that you would be expecting from your compensator. Okay. So here you can see the various responses. And what I like again is that the PID coefficients are automated by the macro. And if I go here to simulator and I go to edit netlist, you can see again here, these are the KE, KD, and KPs, which have been automated by SIMPLIS and that I can reuse in my digital control loop, for instance, to pass as design parameters. So this was analog. Let's look now at the digital solution. So there are plenty of approaches for digital simulation in SIMPLIS. One of them is using the blocks that are available. And there is one filtered PID over here. And I'm going to open the corresponding circuit. So in that case, it's Buck digital PID. And of course, all of these circuits are available as a simulation template. And here, if I double click, you can see that you have to populate KP, KI, KD, and then the different integration method, the derivative method, whether you use just-in or backward or forward layer type of method. And here, the same process is applied. So I manually place my poles and my zeros, and then I instruct SIMPLIS to automate the calculation of the KI, KD, and KP parameters and transform them into discrete values that are going to be passed to the filter here. And if I run again, I think I was looking for, let's see, a 10 kilohertz, 60 degrees phase margin. And if I go there, bias point is okay. And again, you can see 10 kilohertz and around 57 degrees phase margin. You know that there is what we call warping. It means the frequency response of the discrete poles and zeros is distorted depending on the sampling period. So it's probably a little bit at play here. And also here I have included what you can see. There is a delay block here, and I'll come back on it in a minute. So here you see how these PID parameters have been calculated by SIMPLIS here and passed then as values to the subcircuit before simulation. The delay can be modeled using a delay line, but there is none in SIMPLIS. So I've used what we call a first order PADE approximant. It's actually mixing a right half plane zero and a left half plane pole, which are neutralizing each other in terms of magnitude. But because here the right half plane zero is lagging in terms of phase response, then obviously the two phases combine from 0 down to minus 180 degrees. And the total delay at the end is here. This is an analog PWM, so there is no delay linked to the duty ratio elaboration. So that's the delay that I'm creating. Okay, and you can see the various responses here. Let's see now something that I use also quite often, and it's fairly easy here. It's the Monte Carlo process with the Buck VM again. So you know that all these parameters here, the component value, are going to be affected by tolerances. Also because the value itself is going to change depending on the production lot or depending on the temperature. So you have to make sure that when all these elements, especially the ESR of the caps or the capacitance itself changes, they do not affect the crossover frequency. And it's simple here to affect various distribution laws. And then here, that's perhaps not the most difficult, but the thing that you may have to dig a little bit to find them out. These are what we call the goal functions. And the goal functions are probes specifically tailored to extract the crossover frequency, the phase margin, and the gain margin. And if you go to Monte Carlo here and you say set up Monte Carlo. I'm asking here for 10 steps, so it's fairly easy and fast. I'm using the 4 cores of my computer. And if I go then and say Monte Carlo, run Monte Carlo, let's see if it works. So it's going to go through different iterations, say having more or less pseudo-random type of values that is going to affect to the compensator. And then in the end, there you go. You can see how the gain margin is distributed from 31 dBs up to 34 dBs. Then I can look at the phase margin, so it's fairly stable. The phase margin is going to change between 64 and 72 degrees. And then the crossover frequency probably is also fairly stable between 5 and 6 kilohertz. So it's easy to make sure that your power supply, at least on the paper, is fairly robust. And it would be a pity not to go through this type of exercise, because truly it's easy to set up using SIMPLIS. Okay, and when you do that, at least you have a fairly good assumption that the design is robust, at least on the papers, as a first approach. Okay, so this is the way you create the arbitrary probe. You go through this circuitry here. The goal functions are already written and made available from SIMPLIS, so it's easy to pick the one you want, so like gain margin and phase margin. And then once you place them on the circuit, it's easy to collect the results. Very quickly now, let's go on PFC, because the PFCs are big application portion of SIMPLIS, and I'm going to show you how fast it simulates. And this one is working on the demo version actually. And let's see what circuit it is. It is a boost CCM variable T-off. So boost CCM variable T-off. That's the one here. And it's a circuitry that has been made popular by Sam Benyakov in a paper that he published in 1998. It's a kind of predictive type of PLCs where you see there is a current loop here. It's sensing the negative, the current which is going here. And there is this resistance here at the front end that is collecting the inductor and the total current. And then it's by changing the slope of the charging capacitor, it adjusts the off time to modulate the circuit, to modulate the whole thing along the main cycle. If you simulate this time of circuit, at least if you would like to have a few main cycles, so it means maybe 400 or 600 milliseconds, it will take ages before it actually delivers the results. And also the granularity, if you want to look at the various switching transitions, it's going to be hard to obtain something meaningful. Here, what is very cool is that I can put an AC source here, and if I press, let's see, this guy here, you will see immediately how fast it simulates. And with that in mind, I can immediately obtain the results. And again, let's say go and explore different compensation strategy to see how it does affect the distortion. Okay, so you can see how fast it is. It's impossible to beat with a SPICE simulator. Okay, so let's close that one. Something I've really liked is the fact that this source here, you see, is actually an AC source. And if, it's important to note, if the switching frequency of this circuit is fixed and is a multiple of the mains network, then you can run POP analysis using the PFC, and it goes fairly fast. And then you can extract the AC response of the power stage and then run any macros you want to stabilize the loop for, let's say, a crossover of a few hertz. It's very, very efficient. Okay. Something popular we see in the high power field is multi-level PFCs, and here it's a three-level PFC. So what people do is they stack up DC-DC converters, and then they run them either in series or in parallel here, and it helps reducing the stress on these upper and lower stages by having two different let's say stacked voltages, let's say from 0 to 200 and 200 to 400, and it helps reducing the stress. It's very popular in EV charging for high power supplies. The Vienna rectifier, for instance, is a three-level type of circuit. And SIMPLIS can simulate that. And you can see here that's a three-level type of circuit. And I'm using, in this case, it's no longer a predictive type of approach. I'm using a multiplier. And you'll see again how quickly it can actually simulate. So this one is, let's see, boost PFC one phase three-level. Boost PFC, where is it? one phase 3 level. I think it's this one. So let's go. And here I'm going to run the POP using the AC source. So it's only the POP. I don't want any AC. So you see 21 period. And if I go run, again, such a complexity would require a tremendous amount of time using a SPICE simulation. You will see how, okay, it's absolutely impossible to beat in terms of simulation speed. And once I have this guy, I can explore the various RMS components going through the output capacitor. I can use the conduction losses on the switches. And then I can look at, let's say if I do IN and press F3, I can look at the harmonic distortion of the current, and I have 3.4% as harmonic distortion. Again, it's automated. I could explore different crossover frequency and see that if I push crossover, then I may have more ripple coming in, and then it's going to affect the distortion. So as usual, it's a trade-off between transient response and the distortion you want to look at. Okay. Let's try to see. That's the way I've built the multiplier. Okay, there are different techniques, but the one I'm using here, and I'm using the Neperian logarithm, if I pronounce this correctly. And then I transform A and B, my input V in and V in 1 and V in 2, into logarithm that I'm going to sum, and then I take the exponential of the result to create the multiplication. The only difficulty here is, of course, you would like to have the best granularity, but the more steps you're going to have, the more time consuming is going to be, and the more burden on the computer. So you have to reduce the dynamics and also the precision, of course, on the multiplier. And when you go there, you can see what we have seen before. The boost TP-PLC, there is one also here that has been simulated, and it's the same structure. You have a fast leg here. The slow leg is non-synchronous, and I'm not going to simulate it because it's going to take a little bit of time, but it's also basically available as a template. And something I would like you to look at, and I think it's starting here. First of all, it's a small AC-AC type of circuit. I've seen that quite often in the field right now. It's used a lot in solar application. It means if you have excess energy from your solar system, you would like to store this excess energy into a boiler, a hot water boiler. So what this type of circuit do is that it exactly sizes the amount of voltage that is going to be applied to the AC load to exactly absorb 50 watt, 100 watts, 2 kilowatts, depending on the excess of energy. And if you run the simulation here, I'm going to look at this very quickly. Let me see one buck AC-AC converter. It's part of the template. Buck AC-AC converter, full version, it's here. And if you run, it's an open loop circuit, very simple in this one. Okay. And here you can see the nice, it's an AC to AC converter. It's actually a buck converter, which is bidirectional. So either one of the switches here, let's reduce a little bit. One of the switches here is permanently closed for treating the positive cycle. And once the mains polarity changes here, then the one that was permanently closed is switching, and the other one is switching while the old one is permanently closed. And you can see how you have a nice sinusoidal waveform over here. Then the last one, I think I'm going to show. Okay, so in this circuit here, what we see, it's something that I published a paper a few years ago into How to Power. I wanted to show that the instability in a current power supply, and that's something that has been shown by Ray Ridley in his thesis, but I wanted to simulate it actually. The instability and the subharmonic poles you can see in the control to output transfer function of the voltage loop of a current power supply is linked to the lack of phase margin you have in the inner current loop. Okay, and the inner current loop is actually the peak current inductor current controlled by the duty ratio. So it's IL over D, and these values are discrete values. Okay, there's no way you could simulate that using an average model, for instance, because these are discrete values. And What I wanted to show is how we could use SIMPLIS for reproducing what Ridley has shown in his thesis in 1990, using what I've called a digital modulator. So we will see what it means here. But you can see that here that quality factor of the double pole here depends on an artificial ramp level and the on slope of the inductor. So here it's a buck converter and it's running open loop. However, the current loop is closed here. So you see that by changing the amount of slope compensation, you change the control to output transfer function, and the subharmonic poles, which are located here at alpha of the switching frequency, are more damped as you improve or inject more slope compensation. So how can we, let's say, first of all, where does this instability come from? I say it's coming from the inner loop, but how could we visualize that? And actually, there has been a paper in 1986 where some folks from Virginia Tech were showing how to implement what we call a digital modulator, which allows to cut the loop between the drive output here, which is a square wave signal, and the drive signal driving the switch. So this is truly, we want to interrupt the path here and slightly modulate the duty ratio with to inject the perturbation. Why can't we go through the classical AC modulation? Because these are discrete signals. Okay, we cannot just cut the loop and insert AC modulation. It wouldn't work properly. So what I've done here, I've actually modeled a digital modulator very simply. So when this guy goes high, then dx immediately follows. But then when this guy goes down, then I start let's say a capacitor charge, which is here, whose threshold of this comparator is going to be AC modulated by my AC signal. And by doing that, I'm slightly delaying the reset signal, which is going to bring dx down. Okay, and this has been published in How to Power, I think it's 2021. And if that's the way you would insert the modulator. So let's have a look at it. So we go to, it's not in the templates, but I'm going to make it available. So it's in Buck CM. Oh, sample analysis, sorry, and that's this guy over here. So you can see it's a fairly simple switching circuit. It works on the demo version, and here I'm going to put a compensation ramp equal to 0. When you put MC equals 1, it means there is no slope compensation, right? You can see external slope MC minus 1. So if MC equals to 1, there is no slope compensation. If I run this circuit, so first of all, the operating point is 5 volt, as I expect, and then let's see. There you go. This is what we have here is the peak inductor current to the duty ratio control. That's what the modulator here is giving to me, and this is what the body box here is going to extract. And you see that the crossover frequency is fairly high. It's about here we are about something like 47 kilohertz, and almost we have a very small phase margin, right? From 0 minus to minus 360 degrees, almost no phase margin. So if we run this circuit, we may end up into an instability. Now if I improve, let's say, and add something like 20% or let's say directly 50% phase margin, what I'm going to do, there you go. I've slightly reduced the output voltage, of course, because I have less peak current. You can see what I've done. The phase response is the same. However, I'm pushing the curve gain down, forcing a crossover value here around 20 kilohertz, where the phase margin is more favorable. So by injecting slope compensation, I'm actually cheating the current loop, making it believe that the sense resistance has increased. And because the gain of the loop is 1 over our sense, then by injecting more slope compensation, I'm actually pushing down the gain curve, forcing a crossover frequency at a more favorable point where the phase margin is better. And by doing that, I am stabilizing my switching converter. And you can see here exactly how it goes. Actually, here, if we go through the analysis, we see that the 2 zeros are going up here. There is a bunch of a pair of right half plane zeros, which are located at half of the switching frequencies. And these two right half plane zeros, when you close the loop around the inner loop featuring these two zeros turn into two subharmonic poles located at half of the switching frequency in the control to output transfer function when you change the error voltage and you look at the output voltage. Okay, so by injecting slope compensation and using a digital modulator, you see actually the effect of the slope compensation on overall stability, especially the inner current loop. And that's all I have to show. And I thank you very much for your audience, ladies and gentlemen.
Oh, wow. That was amazing. Thank you very much. So that was a little sip from the fire hose, but you can see that there's a lot of great work available there.